Welcome to part 2 of podcast lecture on nanophotonics. This will consider electromagnetic interaction with matter and metal nanoparticles. This is the outline of chapter 8, which is on nanophotonics. Due to the corona shutdown of classes, I decided to split up the material in 4 podcasts as sketched here. I gave an intro to the field in part 1. This is part 2, where I will deal in general with electromagnetic interaction with materials and include nanoscale metals, while part 3 will be on nanoscale semiconductors, and then part 4 on near-field light optical tweezers and optical crystals. So this is the outline of part 2. I'll start by the interaction of photons or electromagnetic radiation with matter, primarily light. That should be a refresh for most of you that dealt with it in MENA 3001 and also in MENA 1000. I will remind about the common interaction processes, absorption, scattering, and so forth. We will also tell about the common optical parameters, permittivity, and refractive index. Again, that is a refresh from MENA 3001 this year. But the theory the book uses describes this as complex numbers, so we will do that here. Then it is important to understand if and why these electromagnetic interaction yields different results for nanoscale material than in bulk. This podcast will introduce what we call plasmons and will emphasize metal nanoparticles. We first look upon the interaction of electromagnetic radiation or light with atoms. We have sharp absorption and emission spectra for atoms. It is observed for gases or atoms. We see a schematic drawing of absorption for an atom. A photon is coming in, hitting the atom, and gets absorbed. The energy of the photon is transferred to an electron that then changed its orbital. We then have the reverse effect for emission. Here the atom is excited. It has 1 electron in E1 and 1 in E2. It can relax to the ground state by emitting a photon which energy is E2 minus E1, when the electron goes from E2 to E1. For solids, it's somewhat different because the electrons have energy bands and gaps, and then also get absorption bands, not lines. For pure semiconductors, we get no absorption for photon energy less than the energy gap. Here we see absorption versus wavelength for common semiconductors in half-log plot. There is negligible absorption for photon energy is lower than the band gap. This is long wavelength. And then a rise at the band gap energy with increasing energy. The sharpness of the rise is higher for the direct band than for the indirect band. This thing called indirect band gap, what is that?
I don't know.
Oh, I think you do. Look here in the figure to the left. This in the bottom curve is the valence band, while this blue curve is the conduction band. Here it is for a direct bandgap semiconductor, and here it is for an indirect bandgap semiconductor.
You're right, I knew that.
So for a direct bandgap, the minimum in the conduction band occurs for the same K as where the valence band has a maximum, while in the indirect bandgap, the points are for different Ks. What is K? That's right. So for a direct bandgap semiconductor, the absorption of a photon with the bandgap energy is stronger than for an indirect bandgap semiconductor. The reason was that the momentum of the system has to be conserved in the absorption process. If both minima occur around k equals 0, momentum conservation can easily be satisfied because the momentum of the photon is small. On the other hand, for an indirect semiconductor, the momentum of the conduction band electron is considerable. It is h bar k, with k for the electron as you said, while the momentum is small before the absorption. In order to conserve momentum, we have to include something else in the absorption. typically a phonon. Then there will be 3 particles in the absorption process for an indirect band: photon, electron, and phonon. The probability for that is much smaller than the probability for 2, as we have for a direct band gap. For metals, a photon can also be absorbed by exciting an electron from an occupied state to an unoccupied state. But there is no threshold energy for the photon. The metals have energy bands, but there is no absorption gap when going into the infrared. We will see later that we also should consider collective excitation of many electrons, not just one by one, for the details of the optical response in the visible and the near UV. I showed the absorption coefficient. Often it is the extinction coefficient that is measured or considered. It has contributions from absorption and scattering. Considering that we have photons coming from the left and falling in upon a slab of material, we determine the extinction coefficient by seeing how many photons are in the beam of photons going out of the slab to the right. Some of the photons entering the slab are lost by absorption. They may excite electrons in the slab. Some photons are lost by scattering, changing direction. Let's go through the argument for deriving how the intensity of light varies with the distance x from the surface. We consider a slab of thickness dx. We consider stationary situation and consider number of photons per time. And we ask how many photons are lost by absorption or scattering in the slab. We call that dn. See the top equation. It is natural that it is proportional to how many photons fall onto the slab, NOx, and also proportional to the delta x, the thickness. We call the proportional constant for Cx. The negative sign is because we lose photons. We can integrate this and we see that the intensity falls off exponentially with distance. Sometimes for a single crystal semiconductor, the absorption dominates completely over scattering. If we, for example, have metal nanoparticles in a dielectric, scattering is more noticeable than in a homogeneous material. I will make some comments on how the common interactions of light with matter will change for nanomaterials versus bulk. In very broad strokes, there are many special cases we will talk about specifically later in Chapter 8, but also in other chapters. You have now already learned that the electronic structure and band diagram will be modified when going from a bulk material to a nanoparticle, nanowires, quantum wells, or dots. That is because of quantum confinement and also increased surface to volume ratio, and the atomic and electronic structure of the surface can be different than that of bulk. The difference in electron structure will lead to variation in absorption. We typically get spectral range changes such as blue shifts and also shift in cross-section per mole. As the dose is changing, the number of states per energy interval. For that reason, we can also expect emission spectra of nanomaterial to be altered, pronounced for semiconductors. There are other reasons, which we will deal with specifically later. As for refraction, that the light will be bent when going from one optical medium to another is caused by the speed of light being different in different materials. We understand diffraction classically from Huygens principles. It may not be convenient to deal with the refraction in nanostructures smaller than the wavelength, but many applications of nanostructures are made up as inhomogeneous medium. So we may treat the system as an effective medium with a composite or effective refractive index. Inhomogeneous materials may also yield scattering. Individual nanoparticles may scatter the light. The photons change direction, possibly also wavelength. We have Rayleigh scattering dealing with scattering from nanoparticles. It is an old theory. We see it has very strong dependence on wavelength, The cross-section is going as 1 over lambda to the 4th power. It is also varying with the 6th power of the particle diameter. Mea's scattering theory is for a little larger particles, around the size of the wavelength. Then we have Raman scattering, involving photons in and out under an interaction with a phonon. The photon changes energy by emitting a phonon and experiences a Stokes shift, or is absorbing a phonon and get an anti-Stokes shift. The Raman shift, the h nu 1 minus h nu 0, can be characteristic for the material by the material having specific optical modes of the phonons. The momentum and the energy is conserved in the process, so in bulk material, the phonon modes involved are at the center of the brilliance zone. For nanoparticles, the phonons are confined to the nanoparticle, thus the location is well defined. Then from the Heisenberg uncertainty principle, the momentum cannot be well defined, and we will get contribution from other phonon modes than those at the center. Someone gets a shift and broadening of the Raman signal, allowing us to measure the size of the nanoparticle. Then let me comment on surface effects. It may influence the other effects as mentioned, absorption, emission, and scattering. A surface will by itself contribute to electronic states. We know that a perfect periodic lattice will yield energy bands and gaps. They are delocalized states, block states. At the surface, we terminate the periodicity and we will get localized states there. Then there are also modes of electromagnetic waves that have states that only exist close to the surface or interface. Then we will also consider later surface plasmons. Now I specifically will deal with the interaction of light with metal nanoparticles. This is an important topic in the course. I will start by telling the history of metal nanoparticles in technology. Then I have to refresh on parameters used to quantify the interaction of electromagnetism with matter, namely permittivity, which you know from MENA 3001. But this time we will use complex numbers. Then I'll talk about plasmons, which are important for the optical properties of metal nanoparticles. You have to know the concepts. I'll talk about the history of metallic nanoparticles and their color. When metal nanoparticles are added to glass, they can give it colors. You know this from stained glass paintings in churches. The technology has been known for a long time. Here is shown the famous Lycurgus cup from the 4th century. However, the understanding of the technology is a lot newer. It was not before Faraday in 1857 documented his systematic study that colors of nanoparticles were understood to depend on the size of gold nanoparticles. Before that, it was believed that the color of a material did not depend on its size. I think Faraday was an interesting guy, also a genius and an idealist. He did not have the opportunity that you students have for education. He started as a bookbinder apprentice in order to be able to read interesting books. That caught his interest for natural science, and he spent his money to go to evening lectures held around London for the public by university professors, against admission fee. After showing a professor a good job he had done at binding his physics book, he got an offer to be a cleaning lad in the lab of the professor and started doing his own experiments. And he became an excellent scientist. Here are some gold nanoparticle emulsions just like Faraday made. We may ask here, why does the emulsion with the largest gold particles appear bluish? And why does that with the smallest gold particles appear reddish? Or even, why don't all of them have golden color just like gold?
Good question. Will you tell the answer, please?
I will start a long answer by having a look at the interaction of electromagnetic waves with matter a little closer. These parameters are calculated in a simple theory. Light is considered as an alternating electrical field interacting with matter. So first we consider the interaction of an electrical field, DC or AC, with matter. We need to consider displacement D of the material when influenced by the field, E. That is described by the permittivity, epsilon, of the material. Permittivity describes how much electric flux is generated per unit charge of the medium. A high flux exists in a medium with high permittivity because of polarization. For light, we need to describe an alternating electrical field, having components varying sinusoidally with time. We describe that by complex numbers for easy calculations. Unfortunately, there are two conventions, physics and engineering, for describing waves as complex numbers. You can alternate between them by replacing j with minus I in the exponential. It's often mixed up. I do that all the time. Here is shown how the permittivity is defined by the ratio of the displacement D and the electrical field E. For a time-varying field such as light, we can describe E and D as complex numbers. However, D may not be in phase with E. There can be a slight time delay in the material's response to a change in E. Then the ratio will be a complex number. So the permittivity has a real part epsilon prime and a complex part epsilon double prime. For a material, the parts will depend upon the frequency as shown in the graph. In a material, we have different things that can be polarized: dipoles, atoms, or electrons. It varies with frequency because, for example, dipoles are not able to follow at high frequencies. For the frequencies of light, only the electrons are able to follow. The real part of the permittivity tells how much energy is stored or propagating in the material, while the imaginary part tells about the absorption or loss. Many used to call the permittivity by the name of dielectric constant. The official standard name is permittivity. The book calculates the permittivity by assuming a simple model for a bulk metal. The considered system have free electrons and fixed ion cores. That is essentially a plasma and is the Drude Sommerfeldt model. We introduced the quasi-particle Plasmon that describe collective excitation of electrons in the metal. When a time-varying electrical field acts upon the system, it will be excited. The system will have a resonance frequency, the plasma resonance frequency, omega p. The next slide will show the book expression for the permittivity in terms of omega p. Later we will see that nanoparticles also have plasmons that depend upon particle size. Here is shown the expressions for the complex permittivity in the simple Drude model. It depends upon the angular frequency omega of the light. The plasmon frequency omega p enters into the expression. It depends upon the electron concentration Ne and the effective mass of the electron m star. Notice the similarity of the expression of omega p to the frequency of a harmonic oscillator consisting of a spring-loaded mass. That has a resonance frequency that equals the square root of k over m, where k is the spring constant. In the plasmon case, the restoring force is a Coulomb force dependent upon the electron concentration. So it makes sense that it takes a similar place in the expression as that for the harmonic oscillator. Further, if the electrons have a small effective mass, they are easy to move, just as m in a harmonic oscillator. The graph shows the amplitude of vibration for forced oscillation of a harmonic oscillator around the resonance frequency for different dampings. The imaginary part of the permittivity, epsilon double prime, tells about loss. It contains a factor gamma that gives the damping. It corresponds to an inverse scatter time for the electrons. Let's test that simple Drude plasma model compared to experimental measurements for silver and gold. The two graphs on the top shows for silver the comparison of theory and experiment for real and imaginary part of the complex permittivity. It is perfect for the real part and has the overall right dependence for the imaginary part, so the model has some merits to it. However, it's not so good for complex permittivity for gold. This is due to band structure of gold. The Drude model does not have scattering between different bands. If one includes interband scattering in the absorption, one gets the right dependence for gold. Now look at a metal nanoparticle. The particle may be so small that the electrical field from the light will penetrate through the nanoparticle, not be completely absorbed. The electrical field will tend to polarize the material, push the electrons. The result is that we get charges on the surface of opposite polarity. That will actually work as a restoring force, similar to a harmonic oscillator. If the frequency of excitation light is in resonance with the eigenfrequency of the collective oscillation, even a small exciting field will lead to strong oscillation. The magnitude of the oscillation then depends only upon the damping involved, which can be both radiative and non-radiative. The resonance frequency is mainly determined by the strength of the restoring force. Force depends upon the separation of the surface charges, that is the particle size, and depends upon the polarizability of the medium between and around the charges. The alternating surface charges effectively forms an oscillating dipole, which radiates electromagnetic waves. This simple model for particle plasmons is reminiscent of an optical antenna. Let's check that we understand it intuitively. A particle size getting smaller gives a smaller separation. That gives a larger force per charge, so gives a higher frequency. Then, when the particle gets smaller, the resonance gets smaller. That has to do with relatively more damping by more often scattering with surface. These tendencies we see in the figure at the bottom. Just to emphasize the analogy to a harmonic oscillator for the metal nanoparticle. We see a peak in the response versus frequency. The width of this peak depends upon the damping. A high and narrow peak has a high Q, quality factor. Much damping and it gets broader and gets smaller. Some words about damping. We can have damping due to radiative loss and due to scattering. These involve transition between electron states. We can have damping due to interband and intraband transitions, as shown in the figure to the bottom left. We talked about these transitions for the case of gold. So one can vary the absorption by varying the size of the metal nanoparticle. One can also have different metals or mixed metal composition and distribution in the nanoparticles. This kind of core shell structures tend to be popular. Here we see in the figure the extinction coefficient as a function of wavelength for different shell thickness but constant core. One can vary the spectral absorption and color. We have only been talking about the color of metal nanoparticles, and we are referring to plasmons. There are many other interests in plasmons and nanostructures, so much that it constitutes a separate field, Nanoplasmonics. It can also be mentioned that there are thoughts about using Plasmonics in computer chips, and even all Plasmonics computer chips for the not so far future. The reasoning behind have been that all electronic computing has a speed limitation due to electrical signal transmission in metal lines. All optical computing can have superior transmission speed, but most functions cannot be smaller than the wavelength of light, which limits packing density severely. For plasmonics, the confinement can be made very small on the interface between metals and dielectrics, and the signal transmission speed is orders of magnitude higher than that of metal wires. It can be interesting to see. The next podcast will be about semiconductors. See you.